Okay, welcome again to our journey into complex analysis, and we've essentially completed what the differentiation theory, and now we're going to move on to integration in the complex plane, which is, you'll see, somewhat different to what happens in the real world, and there's quite a number of interesting surprises here. But we're going to start off with integration along paths, and of course back in the real world when you did simple integral definite integrals, you were integrating with a variable moving along the real axis, and so you were rather limited in what it could do. In the complex plane, we can integrate along paths in the argand plane. So we begin by defining what we mean by, firstly, a simple path from a point C, from a point ZA to ZB. Well, I'm just going to define it as a continuous arc which does not intersect with itself. And such a path has a direction, and we'll consider general paths to be the union of simple paths. A closed path is one which returns to its starting point. In other words, ZA equals ZB. So just a simple example, there's a nice simple path from ZA to ZB, and there is a closed path here, C. In fact, this one here, we call these paths C or gamma or something, so I'll just call that C. We're going to start out by looking at these, and we're going to see fairly soon that the interesting paths to look at are these closed paths. I mentioned in passing this following very plausible but in fact very deep result, which is in fact very hard to prove, and it simply says that a simple closed curve divides the complex plane into two regions, intuitively what we call the inner, the interior and the exterior. And we're going to adopt the convention that the positive direction around a simple closed path is one that keeps the interior on the left. If unspecified, this is the direction we mean. So our definition of path also allows retraversing of the same route. So, for example, we could take this closed path. We start off, say, here. We go around here, looking always on our left. That's going to mean this is part of the interior. We then move along here, again keeping looking on our left. We can then move up around here, looking around on our left, around to here, back to here, around here, and back to where we start from. So that's going to give a closed curve, and that's going to mean that this little region in here and this little region in here are what we're going to call the exterior, and the interior between them is going to be this bit here, the bit that is always on our left as we go around the contour. Now, a simple path C from ZA to ZB is said to be parameterizable, which is just a fancy way of saying that I can describe it using one variable. If each point Z can be written as Z is equal to phi of t, this is the real part, plus I psi of t, for some real t. So this is really, should have perhaps a script R for the real numbers here. So where phi and psi are real functions. For example, the path from 0 to 2 along the parabola can be parametrized in a simple way. We just put x as t, y as t squared, and we simply let t belong to the set 0, 2. So rather the interval, I should say, from 0 up to 2. The unit circle can be parametrized. I'm going to put a spelling correction there. The unit circle can be parametrized in the usual way. We use the trig functions, but much better way of parametrizing in the complex plane is to write the unit circle as z equals e to the it, where t is from 0 to 2 pi. Now, to avoid the path turning back on itself, we're going to require that the derivative of t not be 0. Parameterizations, of course, are not unique. And we might just have a quick look at doing some parameterizations, some examples of parameterizations, because these are quite important. So, firstly, the circle mod z minus 3 equals 5. This is a circle of radius 5, centre 3. So I can easily parameterize this by simply saying, well, if I've got a circle of radius 5, it's going to look like 5e to the I theta. And then I'm just shifting the centre, so I'm just going to add 3 on. And that'll give me a nice parameterization if theta goes from 0 to 2 pi of this circle. Now there's a standard way of parameterizing line segments, and we basically think of it in terms of vectors. So I want to parameterize the line segment from minus 2 plus I to 3 plus 4i. And I'm going to parameterize that by, well, I'm just going to take the first point, which is minus 2 plus I, and then I'm going to take t times the difference of the two complex numbers. Essentially, I'm just thinking of the complex numbers as vectors. And then if I insist that t go between 0 and 1, well, if t is 0, I get the starting point, and if t is 1, these cancel, I get the finishing point. So you can see that it's a very simple parameterization, and it's the canonical one that is the easiest to use. And I can simplify this expression in here, which gives me 5 plus 3i, and then it's often useful to split this up into the real and imaginary parts. So in terms of the previous page, this is my phi, this is my psi, and then again t is restricted between 0 and 1. So third example, just to do the parabola y equals x squared from say 0 up to 2 plus 4i, followed by then by the line segment of 2 plus 4i up to 3 plus 5i. So the picture's looking like this. We're going from along the parabola, and then we're going along a line segment. So we do the parabola firstly, and the parabola again is, keep it simple, I like it to be fairly easy. I just put x equals t, and then from above y equals t squared. And I then let t go from 0 to 2, so when t is 0 I get the origin, and when t is 2 I get 2 plus 4i. Now for the line segment, I do what I did before, except now we've already taken t from 0 to 2. So I go to the starting point, plus, I'm going to subtract the two complex numbers, thinking of them as vectors. And instead of having a t here between 0 and 1, because I'm starting at t equals 2, I replace this with t minus 2, and then let t go from 2 to 3. And again, I'm just going to simplify the expression in there, and then split it up into the real and imaginary parts. So we can then glue these together. We can write down the full parameterization then, so z of t is t plus it squared if t is between 0 and 2, and t plus I, t plus 2 for t between 0 and 3. So just an example of some of these parameterizations that one can do. Okay, having got our parameterization, we want to then define what we mean by a path integral. And there are a couple of ways of doing this. One can simply give a formula and say I'm going to define the integral to be the following, which I'll get to in a moment. But in order to get to be able to do a little bit of theoretical background to it, I'm going to take a slightly more complicated approach. So we're going to consider a continuous path, again, C from ZA to ZB in the complex plane, and I've got a complex function f. And we define the line or path integral of f along C as follows. We're going to subdivide the path into small pieces, Z1 up to Zn. So that's Z1, Z2 and so on. Divide them up into small pieces. Choose in each piece a point Wi. So the W is going to be f of, I choose a point Wi in each of these little regions here. And I'm going to write delta of capital delta Zi to be the difference, Zi plus 1 minus that, which is simply measuring a vector between each of these. And I'm going to form the Riemann sum, which simply says you work out f at each of these values wi in each region, and you multiply by delta Zi, and you sum, say, from I equals 1 to n minus 1. And each of these, of course, is a product of complex numbers, each term. We then, of course, take the limit of the above sum as n goes to infinity, and we make the spacings going to 0. If this limit exists and is independent of the choices involved, then we write the line integral of along C of f of z to be simply the limit of this Riemann sum as n goes to infinity, and as the size of the integrals of these little line segments in here goes to 0. Now note that the part C implicitly has an orientation. If we choose the opposite orientation and call the path minus C, then, as you might guess, if we go along the path backwards, then it's just minus going along the path forwards. This definition does not require a parameterization of the path, and the path need not be smooth. It may have corners, etc. In practice, we're going to require our paths to be piecewise differentiable, and the obvious laws of linearity of the integral hold. So integral of f plus g is the integral of f plus the integral of g, and so on. The above definition, while being fairly precise and of theoretical use, we'll use it when we get to the ML lemma, is not a very practical way to evaluate the integral. And so we'd like to do it in terms of the parameterization. So we parameterize our path, as we've done in some earlier examples, by z equals gamma of t, where t is in some interval a to b. Then a small change in t induces a change in gamma of gamma dash delta t, because our delta z. If the sequence z1 up to zn is thus the image of these points t1 up to tn, so for each of these t's we plug it into gamma and we get the values for z, and w1 up to wn is the image of these u1s up to uns, then we just do what we did before. We simply define this to be this term here. In fact, I probably should put a minus 1 here, and I simply substitute in then the wi is just gamma u of I, and times dz, which is gamma dashed, and then as we take a limit of this, we simply end up with this formula here. So in some books, one way of defining the integral is simply to define this to mean this, but here we've derived it using the earlier definitions. So what it says is, to evaluate the line integral, you substitute in for z the parameterization for z, and you replace the dz with gamma dashed dt. You'll then get an integral here in t's, a definite integral here in terms of t's, and you can then integrate. So we'll have a look at some examples of that. So firstly, just to summarize that, if we parameterize this contour C by z as gamma of t, for t in the interval AB, where gamma is differentiable, then this line integral can be evaluated by replace the z with substitute z equals gamma of t into the f multiplied by gamma dash dt. If gamma is piecewise differentiable, then you can split it up into a finite union of gammas, and you simply then define this to be the sum of the integrals along each of the gammas. And we then apply the formula to each of these integrals. A couple of examples. We're going to just find the integral of z dz, where gamma is the path from 0 to 1 plus I along y equals x squared. By the way, these integrals do not have any physical meaning at this stage. If you want to think of them, they're perhaps some sort of four-dimensional hyper area or something, but we're simply defining these formally by analogy with what we do in the real world and with what we do with real line integrals, which you may have seen in several variable calculus. But we don't have any, there's no sense of area here, there's no real meaning to this in that same sense. We're simply integrating this function as z moves along this path. So the first step, of course, is to parameterize gamma by gamma t is z, which is, now parameterize the parabola. I'll put x to be t, and then y is t squared, as we saw in the earlier example, and we're going from 0 up to 1 plus t, so t goes 0 to 1. Gamma dash then is 1 plus 2it, which is differentiated straight through. And then the integral of z dz is, we replace the z with, we substitute in t plus it squared, and we have to multiply by gamma dashed, which is 1 plus 2it dt. We can expand all this out and get this. In fact, what I did, I worked out the real, separate off into real and imaginary parts. You haven't got to do that, but I did here. And then you just go through and integrate each of these term by term in the usual way, which gives me that expression. Plug in the endpoints and subtract, then almost everything disappears. You get a half minus a half. You get an I here, and the t equals 0 gives you nothing. So the value is I. Again, you can't give geometric meaning to this as such. It's simply a formal integral here, done by analogy on what we do back in the real world. Now, we will come back to this integral later, because you might think, well, surely there must be a better way of doing this integral than having to do all this, and we'll see that there indeed is another way of doing this. On the other hand, and that is because this function z here, the function z that we're integrating, is an analytic function. And so for analytic functions, there is an easier way of integrating rather than doing this. On the other hand, for the next example, we have no choice but to do it the way I'm going to do it here. There's no easy shortcut here, and the reason for that is that if you look at this here, you see this is z bar, and z bar is analytic nowhere. So there's no easy way of doing this except by parameterizing. So once again, I'm going to parameterize the line segment in the usual way. I take the first plus t times, I take the difference. So I take 2 plus 3i minus 1 minus I, which gives me 1 plus 4i. Again, and t goes 0 to 1. Now I need to split this up into real and imaginary parts because I need to take the x and the y. So firstly, by the way, gamma dashed is going to be 1 plus 4i. The x is the real part, that's 1 plus t, and the y is the imaginary part, that's 4t minus 1. And when I plug that into here, then I'm just going to get this integral. I have x minus iy, and then we multiply by gamma dashed. What I did here was, that's a constant, so I just took it out, and I just integrated everything term by term from 0 to 1. Put in the endpoints and subtract. This comes out. It's easy to see. We get 1 plus a half's 3 halves, and then minus I, and then multiplying this out, we get 11 halves plus 5i. Now, the following example is extremely important. This one here is an example where C is a path. This one's a closed path. It's from x equals r to x equals r along a circle radius r, centre the origin, taken anti-clockwise. So our C here is going to look like this. There's our C, and there's r and minus r, and we're simply going around the circle once anti-clockwise, and we're going to integrate z to the n. By the way, just observe that n at the moment is an integer. It could be positive or negative. If n is positive, then this function is an analytic function. If n is negative, then this is going to have something, we're going to have some troubles at 0. It'll be analytic except when z is 0. So just keep that in mind for the moment. And we're going to integrate that one. So we parameterize the circle. We're going to parameterize the circle by r e to the it, where t goes 0 to 2 pi. And we just plug everything in. So by definition, this is, we substitute the z, replace it with gamma, multiplied by gamma dashed. So our z was r e to the it, and we were raising that to the power n, because it was z to the n. And we multiply by gamma dashed, and gamma dashed is I r e to the it. Well, we can take out, these are constants, so I can take these out the front and simplify the inside, leaves me with I n plus 1 t dt. And what I've done here is I have expanded this out using Euler, so you just get cos of n plus 1t plus I sine n plus 1t. Now, if n is not 0, sorry, if n is equal to, say, minus 1, then this is going to give me cos of 0 is 1, sine of 0 is 0. So this is then going to give me, so if n is minus 1, I just get this here. So I get r to the n plus 1i times, you integrate 1 from 0 to 2 pi, you get 2 pi. And here we're going to get 0, so that gives me 0 here. And so I get 2 pi I in the case when n is minus 1. And I'm going to get, so if of course if n is minus 1, then this collapses down to 1, so I get 2 pi I. And if n is not minus 1, then when you integrate these, you're just going to get a sine or a cos divided by n plus 1, but n is not minus 1, so that will give me 0 when you integrate from 0 to 2 pi. So this is a very interesting fact here. In the case when n is minus 1, this integral, let me just write down what it is then. So the integral then along our c of z to the n dz is equal to 2 pi I in the case when n is minus 1. Which, by the way, you're sort of thinking, perhaps it looks, n is minus 1, you're sort of thinking perhaps logarithms, and it's 0 otherwise. So that is an important fact we will use later on. And we'll continue with primitives in the next recording.